So I want to raise a question about schematizing the observer within the theory.
Okay.
Because I know it's going to come up again just to get things started. Now, why don't we just think about Newton's measurements of mass in the Principia, which is part of the way he resolves the issue of Copernicus and so forth.
Right.
What does that have to do with locating the observer within the theory? Well, you might think in astronomy, to do astronomy at all, you first think, here we are on the surface of the Earth, what we see initially is these changes of angles of stuff up there. And then we have to get to our astronomy starting from that. What that looks like, what's going on. But by the time you get to the Principia, that's really not an issue anymore because we already have Kepler, we already have Galileo's observations of the phases of the inner planets. We already have some kind of acceptance, at least on Newton's parts, of Kepler's area law. And all of that tells him that the planets encircle the sun, not the Earth. But the planets except possibly for the Earth. And he's left with, well, so is it the conic system, or is it a kind of Keplerian?
Right.
And he settles for the latter by showing you that the center of mass is very close to the solar. Now, that has to do with him developing his concept of mass, relating it to things like gravity on the surface of the Earth, and weight, and so forth, and then extending it up into the heavens and so forth. But none of that directly involves any more worrying about where we are.
Right. So
But that's an overstatement because the moon test does involve that.
Right.
But still, it's not a matter anymore of how do we go from these things that we observe on the celestial sphere, because we've already done that. We've already gone out to Kepler.
Right. So 2 points in response. First is I don't think it's ever the case that we are starting from scratch, and schematizing the observer can be too anthropocentric. So I think it's a better way of describing it is, how do you characterize a certain experimental situation or an observation? And it might be that the theory you're interested in can already rely on a lot of other background theoretical knowledge. And then the question is more like, why is it that you take the orbits of Jupiter's moons as telling you something about the mass of Jupiter, right? Or why is it that you can use a pendulum to measure time, or the strength of the gravitational field, right? So that those are the kinds of arguments where I think the theory dependence, and it's really maybe, think of it in the way Hempel talked about provisos, right? That you have some antecedent vocabulary, and then you have a novel theoretical vocabulary that's introduced. And what I'm talking about is more specifically in how to introduce novel theoretical concepts. You often have to have a very theory-dependent description of the way that those enter in a specific experimental context. And then actually connecting it up to what we observe might have a huge amount of antecedent vocabulary that's added on to that to get to the point of saying, and then I measured the length of the seconds pendulum, and that was the outcome of the observation, right? So so the schematizing the observer is too anthropocentric, I'm sure.
It just doesn't seem to be, at a certain point, it's a story about what George calls theory-aided measurements. And I understand that.
Right.
Which, in general, doesn't necessarily involve putting us anywhere in particular.
Right, and in the cases in cosmology, it's more a question of what exactly is light propagation revealing to you about. So it is really more of a theory-mediated measurement.
Whatever we might be.
Right. But I think the general point is that in thinking about the empirical content of a theory, you need to include some account of how measurements proceed. And I was following Stein and emphasizing a more, schematizing the observer line of characterizing.
Well, I love that notion.
Yeah.
But
Well, yeah, because
I'm just having
continuum.
trouble.
Yeah.
And I'll just raise one other question, which is an obvious one that people always worry about. What does this have to do with the requirement of completeness on a theory? That is, that the theory should contain a story itself of how we measure stuff or how our experience happens. And people often bring that up in quantum mechanics as a motivation of the measurement problem. Right?
So what?
As if
how
the
are
theory
you
itself
characterizing?
had to tell us how we did it, or else the theory's incomplete.
It depends on what you mean by completeness. I mean, I think there is a question about how it is that you describe laboratory outcomes within quantum mechanics, but I don't know that I would want to demand a form of completeness of theory. And so I think I'd have to hear more about what you mean there. So sorry I didn't.
It's all right, we'll come back to it.
Okay.
Hi. So, I mean, I could comment on almost every one of your
I'm sure you
slides,
could.
but let me try to focus on. So, I mean, I would think that in, the theory of cosmology, I mean, the standard model, I mean, one has this model that includes, a description of the inhomogeneities, at least the statistical properties of the inhomogeneity. So I would think the question is, well, there are two questions. One is this model even self-consistent, given we have Einstein's equation, and with the inhomogeneities, that isn't necessarily obvious that that it would be. Excuse me. Okay, so well, let me start with this. So I mean, within what I was trying to get to, and which I forgot momentarily, is then, given the standard model, what would an observer in the universe see, at least statistically, and is that consistent with the observations? And if it's consistent with the observations, and in fact is even much better than that, it agrees with high precision with the observations, then I think we should be happy. Now, it would be useful to picture a ball bearing on the surface of a real ball bearing, and one could ask the question, how well is this ball bearing described by a sphere? Okay, well, I claim in the standard model, the universe is described by, the metric of the universe is described by an FLRW metric to better precision than industrial standards for a ball bearing is described by a sphere. Okay, now you talked about all these big inhomogeneities that we see. Oh, okay, that's in the matter. I mean, if you look at a ball bearing on fine scales, you'll see a lot of imperfections on fine scales, and by the time you get to atomic scales, you really see a lot of imperfections. In the real universe, by the time you get to atomic scales, you see density inhomogeneities that are a lot larger than what you're talking about with galaxies, and so on. Okay, but there isn't a fitting problem. I mean, if the standard model is right, I mean, the universe is incredible. The solar system, similarly, is very well described by a flat metric. Okay? It's very hard to do a measurement in the solar system that would directly measure the metric and show,
Right.
light
Yes.
triangles or whatever you want to do, and checking that, light, okay, I shouldn't do that because that's geodesics and so on. I mean, the thing is that derivatives of the metric are not very close to FLRW, and second derivatives of the metric, curvature, matter distributions, are way off, which would also be true on the ball bearing, I claim.
Right.
Okay, so anyway, one shouldn't be upset with using the FLRW model, even if the second derivatives of the actual metric of the universe are very different from second derivatives. Now, you have to take that into account. And when we're doing, light propagation to get the redshift distance relations and acceleration, I mean, then we are doing geodesics, and those do differ significantly, but in a perfectly calculable way, given what we know about the density and homogeneities, and that's taken into account. For the distances being used to measure the present value of the Hubble constant, that's a pretty negligible correction. If it was a very lumpy universe and you were going out to large redshifts, and for the acceleration of the universe, that is a that is about a 10% potential correction, which has been fully taken into account in the interpretation of the observations. And I don't see the philosophical issue in there are a couple of separate issues. I mean, would these density inhomogeneities cause a significant back reaction effect? I claim clearly no there are
Right,
other
no,
people who claim yes. I won't get into, or they don't claim yes, they claim maybe, and they're talking about 1% type effects that
Right.
wouldn't explain the acceleration of the universe. I mean, I don't know where they get the 1% from. It is about 1,000th of a percent effect on the expansion of the universe, I think is the correct answer. But that's maybe a little high, but now, I mean, another thing that you mentioned, just to randomly go on while I'm thinking of points, but just one thing to throw in the mix. I mean, this Hubble constant discrepancy between Planck data and present, that's a genuine discrepancy,
Right.
which I think most people, would present, if you were to survey cosmologists, would believe that there'll be some, error in the data analysis or some, correction
Or
that
cosmic variance.
hasn't been taken. So I don't think it could be cosmic. It's too big to
It's
be.
too big to be cosmic
I
variance.
think. But or it could be, a first hint of some new physics or something. I mean, that's a
Yeah, no, people
genuine.
have raised that as well.
That's a genuine problem or issue. I mean, that people I think are very much keeping in the back of their minds as maybe it's interesting, although the prevailing view is that it probably isn't interesting except in terms of how people calibrate, their. But anyway, but I don't see. I mean, the standard model is consistent. Well, I claim is fully consistent with general relativity. It makes predictions, though, except for a few
Right.
little anomalies. I mean, the Hubble constant, that's really a little anomaly. It's just a few sigma off
So-
from agreement, and when you measure it, these different. But I mean, you can point to other anomalies in galaxy formation and so on that, okay. I mean, and maybe it's a hint that there's something wrong, but I just don't see the problem, and I don't see
Well, so let me-
the philosophical issue.
So, so first of all, I don't think that I ever claimed that GR was inconsistent and applied to the standard model, so I'm not sure.
Well, I'm talking about if there were large back reaction effects.
Okay, I see, yeah, so,
But that's
so
all.
let me, so first of all, probably there was a mistake in emphasis. I totally agree that the standard model is overwhelmingly a successful way of modeling cosmology on a wide variety of scales. It's striking how successful it is. The philosophical approach I was thinking, that I was arguing for, is thinking of long-term evidential reasoning. We often demand a lot more of our theories, that we ask exactly how even the small anomalies that we see, now that we have an understanding of systematic errors, that we have confidence that we're not just looking at noise in the data, that we pursue those avidly to possibly discover new physics.
But that's
So-
what people
Yeah,
do. I mean,
and that's
that is,
and that's what I was claiming, that one way of thinking about that is thinking about exactly how are you modeling the measurement, and asking, in describing, say, the way light's propagating through the universe that is reaching us from the supernova, are there physical effects on the way light's propagating?
But those are taken into account in everybody's
Okay, so
simulations of everything.
So how are they taken into account, those sorts of?
Well, mostly they're taken into account by people, doing simulations of galaxy formation, and then within those simulated models, looking at the light propagation.
So tracing light rays
Yeah.
through the galaxy formation.
Yeah.
models. Okay.
Uh,
So then the question, I guess, would be, they've already done that kind of accounting of the measurement where you're actually tracing through local inhomogeneities. And what I'm looking at is another kind of extra claim that above and beyond that, you have to try to model the universe as this sort of Swiss cheese approximation. And you're claiming
Well, I'm
that's not-
saying that the people are doing better, they're taking
right, no, yeah, so
realistic
this Yeah, no, so this
models.
is.
I mean, Daniel Holtz and I 20 years ago looked at a version of Swiss
Okay.
cheese and got all these plots for what the lensing
Right.
effects look like, and if you make a universe out of all black holes, let's say, which is
Right, then
best you
see
could
what
do,
the-
that by the time you get to a redshift of 2 or 3, you're really getting big
big
corrections.
effects. Right, right.
And Daniel, for his thesis, looked at, if you put in more realistic matter, how big an effect would that have on this interpretation of the
Mhm.
the acceleration of the universe?
Right.
And, he found that was about a it was potentially about a 10%
Right.
effect. I mean, you could be misinterpreting things in that sort of range.
Right.
I think maybe we should move on to the,
Yeah.
so Sebastian was next.
Thanks. I have two questions, but since there is no time, maybe I'm gonna ask just one and then I can ask you the other one. So the motivation or part of the motivation of your talk, I take it, or a small part was about the circularity issue at the beginning that you mentioned. And you put it like as a challenge to cosmology in particular. I was wondering how is that challenge different from something like Duhamel's thesis, like in which behind each experiment there is a lot of theory already, and like you might have circularity trying to explain.
I didn't mean to make the case that that was
Special.
a special issue in cosmology. It might be a matter of degree. It might be that certain observations in cosmology rely more on a single sort of theoretical background. In other cases in physics, you might not have that reliance on one and the same theory for all different aspects of an experiment. So it's not, but it's at most a difference of degree, not a difference of kind. So I think that kind of theory dependence is.
Okay. And the second one is then, when you were talking about the Hubble, the discrepancy between these two measurements, and you said, well, maybe they are not measuring the same property, or that's a possibility. I was imagining, like, do you have like a motivation behind that? Because maybe if you say that, each time you get different results by different methods, there is the worry that an easy solution would say, well, maybe there is no discrepancy at all.
Could you put that back up?
Yeah.
Yeah.
You're just measuring different properties.
Actually, I can't
and then-
because you're asleep. Sorry.
That's your,
Learn a lot about it.
There.
Yeah.
Okay.
It's just a general question. If
Oh,
there
right.
is like,
Am I multiplying entities or something when I say that they disagree, or?
oh, like I was imagining if that happens in other cases, like when you think you're measuring the same property and you have discrepancies, and then you say, well,
Yeah.
a solution to this is to say they are not actually measuring the same property.
I think I should probably be more careful in saying, in this case, if something like the account of the effects of inhomogeneity on light propagation is important in resolving this discrepancy, then in some sense you're measuring the same properties, just that your way of measuring it is slightly different. And if the account of the effects of inhomogeneities on light propagation is enough to resolve this discrepancy, then you'd say, well, look, you're both measuring the Hubble flows, just the way light is propagating to you at local scales from supernovae is different. And if you describe that in the wrong way, then you get a disagreement. But if you describe it in a richer theoretical way, then you'll see that these are reconciled. So that would be one possibility. And that's what I was suggesting. I wasn't actually suggesting that we should think of them as completely distinct quantities.
Yeah, thank you.
In response to Professor Wald, sometimes issues are philosophic to people outside science that do not appear so inside. And I've had
Yeah,
two
no,
observations, and one is apropos of that. You won't be surprised, I love that talk, I suspect. One of the things, you danced around the use of the word knowledge, but then you proceeded to illustrate the principal justification for using that word in application to serious science. The constant revisiting, refinement by whole communities. That's a continuing process. So, in a way, you just methodologically demonstrated why you really didn't need to dance around the word knowledge, because you illustrated it as well as it can, and that's why I think from your point of view, there's not a philosophic issue there. But there is to those of us who worry about what knowledge is. Now I want to make a much more important observation. Like this morning, I'm in the process of generating dissertation topics for people. There's a wonderful, wonderful analogous result to what you've just presented. It's the internal structure of the Earth, starting with Oldham's discovery that seismic waves contain information about the internal structure in 1906.
and then this massive continuing process, starting with isotropic assumption, limited resolution. So for example, we still don't know where the liquid outer core mantle boundary is to better than about 15 kilometers. The word I want to use for that one figure is degrees of resolution, which come from observation and the mathematics. But the same continuing process is happening, and it's the same problem of the observer. The observer's not in the middle of this. The observer's sitting on the surface of the Earth at a singularity point.
Yeah.
So it'd be a very, very good parallel example for one of your doctoral dissertation students to.
Yeah, no, I think there's a lot of ways in which that's similar because the access you have to claims about the internal structure are so theory dependent. And,
Absolutely.
yeah,
No,
sure.
no, strikingly
Developing those at the
parallel.
same time that you're developing a greater knowledge of the interior of the Earth. Thank you.
One question about this trouble with Hubble, the Bernal paper, 2016.
Yeah.
You mentioned that as far as looking at, okay, well, what are these two measurements of, right? And what the relation is, whether they are the same thing from different standpoints, whether they should be regarded as two different phenomena. Who is currently doing work? You mentioned there's a group maybe doing work on this, following up on that paper from 2016?
Well, there's Fleury, who's a student of Uzan,
Okay.
and there's a group in Paris. There's I guess papers by Daniel Holtz, you said, from...
Well, that's 20 years ago.
Yeah, yeah,
But-
and then there are several other people doing different types of modeling like this. I'll have to get you references later.
That'd be great.
They don't come directly to mind. So.
Okay, thank you.
Yeah, this is just one case of somebody doing a calculation like this, and there's several. Yeah.
I mean, if I could just,
Yeah.
within the standard model, they're measuring the same quantity, but
Right.
the local measurement really only depends on what's gone on in, the last billion years or so.
Right, right, yeah.
Whereas, the Planck measurement would be sensitive to what has happened,
Right,
since the
yeah.
decoupling, so
Right.
Much more of the, nearly the whole history of the universe. So if the laws of physics, if general relativity were modified so that you had a different expansion rate in the in the moderately early
Right.
universe or something, then that could account for the discrepancy. I mean, that's why it might be a very interesting hint of new
Right.
physics.
Right.
But so they're only the same things within the
The
standard,
standard model. No, that's exactly right.
Am I in the seat?
I
I
can
don't
tell
think Jim
Eric
can
had
see
his,
you, so.
I keep moving around trying to get a
Okay,
sense
alright.
of, but Eric may also have his hand up.
I was trying to decide actually whether to raise it or not, so I was just resting on my
Wait, no,
hand.
Yeah, so this isn't something you, it's related to what you're talking about, but it isn't something you directly touched upon. A number of years ago, people were, some people were touting these Monet-Tolman-Bondi models that have us
Right.
at the center of a sphere, near the center of a spherically symmetric underdensed region, and that would affect the supernova 1A
Right.
greatly. That would affect our estimates of expansion at supernova 1A, and the claim it was that we could possibly get those results without any with a zero lambda.
Right.
And I know at the time, some people were saying, well, look, that requires this ridiculous coincidence that we're almost exactly at the center of the spherical void. But George Ellis was saying, no, what we need to do is get some observations to rule those out. What's the current status of discussion of those things?
I actually haven't followed that closely, but yeah, it's another way of trying to get rid of the need for dark energy without modifying general relativity, but looking at a different solution. And Bob, you're...
Well, I mean, I don't think anybody's pursuing that now that I know of. I mean, I'm not necessarily. I mean, mainly because you could throw away the supernova observations completely, and there's still overwhelming evidence for accelerated expansion just from microwave background and what we know about
structure
dark matter,
Okay.
and so on. So,
Okay, that's good.
this Bondi-Tolman type models were just designed to, explain, and as you said, in a rather artificial-looking way, how you might get results compatible with just the supernova observations. But I mean, if you took that seriously, extrapolated what the universe would look like back near the Big Bang, you got ridiculous answers then. I mean, so it wasn't a very viable explanation then. But by now, it's explaining only one piece of a large array of
And there's all these other estimates.
data, and it won't help for explaining why the cosmic microwave background type data gives strong evidence.
Putting us in the center of the sphere, is that the thing that is the word?
No, the,
Well, no. I mean, that it doesn't help at all for explaining away the evidence for a cosmological constant from these other.
yeah, there's lots of evidence
Way-
that went into the supernovae that indicate.
So if it was, I mean, at the time of the supernova discovery, that was the only evidence for accelerated expansion, and this would have provided an alternative. But now this won't help for the other pieces of evidence.
Eric, briefly.
Yeah, there's an ambiguity in the idea of talking about the model, even if you are even when you introduce inhomogeneities, whether you do it by Swiss cheese or any other way, because it really depends on what exactly you're including in the inhomogeneities, what the fine details are that you may pardon me. You may or may not want to include. You may want to include, for instance, extragalactic magnetic fields, and if you do, you may want to include how they vary or don't vary on different length scales and different time scales. You may want to include or may not want to include intergalactic or nebular dust or intragalactic dust. You may or may not want to include ionization and plasma content. And each one of these is each one of these decisions is in how you construct your model is relevant to your discussion in two different ways. One is that depending on, for instance, what wavelength you're making your observations in, some of these will be important and others won't. And so that's a place where the starting idea of schematizing the observer really becomes crucial. But what then becomes very interesting is that taking different of these features into account and building models in general relativity, or approximations of models in general relativity, taking different physical properties and systems into account and how one constructs the inhomogeneities in any kind of fine detail, actually leads you to several different families of models that are in no way systematically related to each other. The models that include the extragalactic magnetic fields are just not systematically related in any mathematical or physical way to the ones that take the nebular and intergalactic dust into account. And so I'm curious on your picture of this, on your view of how theory and experiment are supposed to be intertwined here. What does it tell us about our knowledge of cosmology? Because, and this is not supposed to be raising skepticism at all. I actually find it quite extraordinary that these people are so incredibly good at doing this and are giving us such amazing observations in the face of such extraordinary complexity in trying to match theory and experiment together. But it does tell us something, but I'm not entirely sure what. I'm curious if you have an idea what it's telling us about the structure of our knowledge in cosmology, that there's such complexity between the fine details of how one chooses the model, depending on what exact kind of observations one is making, and contrarily how that makes the family of possible models, so to speak, the relations among them extremely non-trivial.
Yeah, I mean, I think, I don't have a full answer, but I think often what people are doing are constructing very simplified toy models and trying to estimate the order of magnitude of the effect that including a particular kind of physical process would have on a type of observation, right? Speaking very abstractly. And it is striking that for a lot of the observations, you can have relatively simple models. But as the precision is increased, like there's the kind of things that people have to take into account and deriving parameters from the CMB, it's astonishing. If you actually look at the reports of how they have to do things like take into account galaxy foregrounds, take into account the ionization depth of the plasma. So all that complexity that, as far as they know is necessary, has to be accounted for. And I think it's just that at various stages, they were probably forced to model certain processes because they couldn't account for the phenomena without including that in their model, right? So I think questions like, do you have to take into account magnetic fields at a certain scale? I think you're either pushed to do that or you aren't, right? So if you have a model that allows you to understand the observations and it appears consistent, then maybe with ongoing increasing precision, you'll be pushed to eventually include that kind of complexity. And the overall approach that I'm advocating is that if you actually have an understanding of, a detailed understanding of how the measurement's working, then you can be pushed to remove idealizations by discrepancies. Because if you know exactly what you've put into the model and how important that is on understanding the output you have, then you can say, well, we didn't include magnetic fields, we said that there are 0 magnetic fields, and then you can, if you have an understanding of the measurement account, you can say, well, do we need to, are these sorts of observations forcing us to now include magnetic fields in the model, right? And so I think there is a huge amount of complexity that I've shoved under the rug in the way that these cosmological parameters are already being measured and the sort of data analysis that people are already going through. But the level of precision that cosmology has already reached is astonishing, and people are being pushed to develop more complicated models as a result of the level of precision. And that's just like what we've seen in the development of celestial mechanics and other cases where you have a series of successively more detailed descriptions of one phenomenon. And the fact that you're able to do that without completely abandoning the theory gives you great confidence that you've actually understood the dynamics for the system at hand.
We are, in fact, over time, so we're going to take a short break for the next speaker. It'll be a little bit less than 5 minutes. We'll reconvene at 2:23.